Hello everyone, today I'm going to deliver another lecture on calculation reaction shear force bending moment calculation by moment distribution method for beam. First of all, I will try to cover the theory of the moment distribution method for beam and then give some examples of moment distribution method for beam. So let's start uh, for the theory. So why we need to moment distribution method. So we have been known the when the structure is indeterminate, then we have to go to the moment distribution method or force method or steepness method. So we can what we will find out, we can find out force and shear force diagram and bending moment or of shear force or a moment also. Okay, so let's start. So first of all, have some end moment. I'm just going to this is the book for structural analysis, basic structural analysis, RG ready. Okay, so the moment distribution method is also known as the Hardy-Cross method. It provides the convenient for supplying statical indeterminate beam and frame for simply calculation. Okay, so sign convention as usual case. So we know the absolute and relative stiffness member. As we know, E for EI by L from appendix table we have been seen here. For moment further extend equal to 2a by L and so on. What is the carryover factor? If the moment MIG applied at the end I and the member figure given 12.1, where is 12.1? This is the 12.1. I have been shown. This is the 12.2. Okay, this is the 12.1. And this is the theta, and a specified amount of mj generate the further restraint in, and carryover factor is defined the factor which is the moment simply supported in and is multiplied, m is the multiplied in the gather applied to get moment carryover. On the other hand, m is m over. Okay, so c is given carryover. What is the distribution factor? Sir, some value is given here. So distribution factor, the consider joint is member where two or more member meet. If the external force external moment m is applied in the sub joint, the joint is undergoes rotation shown in figure in 3. Since all the member is meeting at the joint undergo the same rotation is applied, the moment is distribution each and the moment is according to their relative stiffness value, and the factor of this applied moment is multiplied the obtained the in moment any member is known the distribution factor. Okay, so let's see Hitler books what is right his definition. So let's see. It is taken from structural analysis 4th edition by Hitler. Okay, we can see here the concept of moment distribution when the apply method to solve problem involving statical indeterminate beam or frames. Okay, so we have to, when the member is indeterminate, then we can have to solve here. So sign convention, so we've been seen here. The sign convention is given here the clockwise, as we've been seen here. Now the clockwise moment that act is the moment, and the consider positive, and counter clockwise moment is negative. Okay, so this we have been seen in figure. Fixed in moment, the moment at the wall or fixed joint at the loaded member are called fixed in moment. Okay, what is the member stiffness? The member stiffness is considered for but it is when is conjugate beam method, it is also a moment we have been seen 4 ei by L into theta. So as we have been calculating the far end fixed, that's why we have been calculating k equal to 4 ei by L. Okay, so as we know, m by theta equal to stiffness. Okay, so joint stiffness we have been seen here. If several member is fixed connected to the joint and each other far end is fixed, then by the principle of this superposition, total stiffness factor at the joint and is the sum of the member stiffness factor at the joint, we have been seeing kt equal to sum of all k. Distribution factor, if the moment is moment m is applied to the fixed connected joint and connecting member is supply position, the moment is necessary satisfy the moment equilibrium at joint, there is the factor. Testing moment supply on the moment is called distribution factor. So we have been seeing the distribution factor, summation of only stiffness divided by sum of all stiffness. So member relative stiffness factor, it's not needed, so carryover, so it is needed. So consider the for solving theta equation, this equation we get md equal to mb divided ba divided by ab by 2, mba equal to mab divided by 2. In other words, the moment at the pin induce the moment m prime equal to half of the m at the wall. Okay, so we can see the pin moment, this is the half, this is the wall moment, it will be half. The carryover or the repetition of the fraction m, we have been seeing the carryover from the wall, hence this is the beam is with the far end and carryover factor is half. Okay, so we have been seeing here the fixed in moment, so there is some formula we have to must be memorized. When the end support then WL square by 12, then in support is fixed but the load is pin, so PL by 8. In the cantilever, the fixed and UDL WL square by 2, and this is the b square d a into divided by L square, p a square b into divided by L square, and it will be WL square by 12 and it will be WL square 12 and WL square by 30. And this phenomena, then it will be m by 4 m, and for this we can see WL square 12, WL square 10 10 12. Okay, stiffness factor modification k. So if we see when far end is fixed, these are the fixed, then we use 4 ei. In all cases we use 4 ei, and when far end is ruler or pin, then we can use 3 ei, but we are not recommend this. We can use 4 ei for getting the value. When the symmetric beam, so you can see symmetric beam and symmetric load, then it will be 2 ei. When the symmetric beam with the asymmetric loading, so asymmetric loading we have been seeing, then 6 ei. So distribution factor we have been shown distribution k be divided by sum of k. The fixed in support distribution factor is 0. It will be must you can memorize this fixed in 0. And the free end distribution factor 0. The hinge and ruler support distribution factor 1. So you have to must be memorize this and must be memorize this only for ei by L, and must be memorize this formula and this formula. Okay, and this formula also. Now carryover. So carryover always half, sorry, it will be half transferred. Okay, these are our theory. So now we can see the some examples. So let's go to the some example. This is the beam. So determine the internal moment of each support of the beam. Shown the EI is constant and use the moment distribution method. Okay. So we've been seeing here the a structure beam which is A, B, C, D is given. A and D as the fixed and B and C are the pin support. The stiffness factor K equal to AB equal to 4 EI by 12, KBC equal to 12 BI by L is given 12, and KCD is 4 EI by L is 8, 4 into 4 into 8. So distribution vector AB and DC is 0 because this is the fixed support, and distribution vector BA, that means these are the B and this is the A, so it will be covered here. The BA for EI by L, that means B, and the adjacent member which is BA into BC. So BA is 4 EI by 12 and BC equal to 4 EI by 12. As we have been seeing, the distribution factor will be this is the formula. As we have been seeing, distribution factor KAB divided by the sum of K. So as we have been seeing, this is the sum. That's why it is found here. Okay. So in the same way BC, this is the BC. So we are taking the 4 EI by 12 which is BC, and sum of these two member also BC into BA. This is the 5 into 5. It must be 1 because this is the end adjacent and this member or this member contribute 1. Okay. So now see CB. This is the CB. It is going here C to B. So summation of 4 EI by CB divided by CB into CD. This is the CD. So it will be 8. Must be you can keep in mind. And what will be CD? CD will be CD divided by CD into BC. So this is the CD 4 EI by L and CB divided by CC. Okay, we've been found 0.60. So if we adding, it will be 1 because this joint will be 1 in right direction and left direction. The sum will be 1. The fixed in moment AB equal to 0 because AB is a fixed. Oh sorry, AB there is no load in AB member. Fixed in moment there is no load. So in BC member WL square by 2F and found 240, and CD member we have been found PL by 8 and 250, and it will be negative sign. Okay, let's see the joint here. If I take this picture a snap, then it will be easy for us. These are the also same, so I'm just taking the okay, so sorry for that. So we've been seeing joint A. This is the joint A. This is the joint A. AB is a member is AB. This is the member of AB. And joint B. This is the joint B. The member is BA and BC. So BA and BC, and this is the C. This is the C, and CB and CD, and last one is D. So member A, there is no left and right, only right direction. But the joint B, there is a two portion, one is left and another is right. So that's why here is the left BA and BC, and left and in the same point C, and left portion CB and right portion CD. The distribution factor we have been found 0 as the fixed. There is a fixed support. That's why AB is 0 and A 0 and D point is 0. And the other we have been found 5.4 in previously. Here is the distribution factor. We have been found all the member all the points. Okay. So now we are seeing here the fixed moment. How we get this value 0 to 40, 40, 40. So if we go there, the fixed moment AB is 0 because there is no load. That's why this is the 0. But BC, we have been seeing BC 240. So this is the BC 240. and 240 is CB. This is the 240 CB, and 250, this is the minus 250, and 250 is positive, 250 is positive. Okay, so let's see how we'll calculate this value. So this is the, as we know, this is the 0 and 250, so it will be balanced. So if we balance this 250, we have to divide this 250 in each member BA and BC, which is 50% and 50%. So 240 is 50% is 130. If we 250 multiply with 0.50, it will be 120, and it will multiply with 50, it will be 120. It will be minus, it will be positive, because it is the balance carryover distribution moment, balance distribution moment. Okay, so point C. So you can see point C, as we seen here, this is the point C. So there is a two portion, one is left, another is right, which is CB and CD. So CB and CD we have been seen here. The fixed in moment we have been seen here, 250 and 240, as we have been seen CB. This is the 240, this is the 240, and this is the 250. So unbalanced we have been seen 240 minus 250, which is 10. So 10 will be divided 0.60 into 10, which is 6, and 0.40 into 10, it will be 4. So as this is the moment distribution of balance purpose, the minus 10 will be positive, 4 in positive 6. This 2 sum is 10. As like as 120 into 120, the sum is that 240, it will be minus, because this is the distribution factor, but the distribution factor is different, 0.40, 0.60. That's why this is the 6 and this is the 4. Now we can go carryover. So it will be goes the carryover BA into AB, which is 50% carryover always. So as I have been shown here, the carryover will be the carryover always transfer is half. That's why we have been seen here, the carryover we have been seen 120, it will be half percent is carryover 60. And in the same way, so the 4 into carryover into 2, and 120 is carryover is 60. So we've been seen BA into carryover AB. What does mean is, if I open this diagram, so we've been seen our member BA, that means this is the BA member, B2A is going here, and AB, this is the A to B. So this is the A to B. So BA2 is going to the fixed support, which is half percent. In the same way, we have been seeing BA and BC. This is the BC. BC, it is going to B2C. This is the going BC. B2C, which is 120 to 60%, and CB, this is, that means it will going to C to B. So C to B, this is the BC, so it is going 4 into half, which is 2. In the same way, it is going to CD, C to D, which is 6 to 6 into 1 into 2, which is 3. So in the same way, where the second column we have been seeing, this is the 2. So we have to balance these 2. So 2 is 0.5 is 1, and 2 is 0.5 is 1. So as the balance distribution factor, that's why it will be minus. The same way, how we will get 60? So 60 into 0.4 equal to 24. 60 into 0.6, which will be 36. So as this is the positive, that's why it will be negative, because we are calculating balancing moment. Now we carry over 0.5, and this is the 24 into 0.5 equal to 1.2, 1 into 0.5 into 0.5, 16 into 5 or half, we can say, as 18. So in the next trial we have been seen here 12 into 12, so it will be balancing purposes, it will be 50%, which is 0.6, and the 50% of this, it will be 0.6. As this is the positive, this will be negative. So this is the point minus 0.50. So minus 0.50 will to multiply 0.40. I'm just changing color. If you understand here, with the 0.50, it will be multiplied with 0.40. Then we will found 0.20, and 0.50 will be multiplied with 0.60. It will be 0.30. As the 0.50 is negative, that's why it will be positive for balance moment distribution. Okay, now we'll go to the same. Carryover is 6 divided by 2 is 3, and 6 divided by 2 is 3, and 0.20 divided by 2 is 0.1, 0.3 divided by 2 is 0.15. And last we've been seen here in the same way we are distributing here 0.10 into 0.50, which is 0.5, 0.5, and 0.3 equal to 0.40, which is 1.2, and 0.3 into 0.6 equal to 1.1, and then distribution 0.9, and it will be also distribution 0.025, and 0.60 and 0.25. This is the last one. We can see here 0.60 into 0.5, which is 0.30. So 0.60 into 0.5 into 0.30, and this one 0.025 into 0.40, it will be 1.01, and 0.025 it will be multiplied 0.60, it will be 0.05. We can stop here. We don't need more trial because it is coming for close to the 0. That's why we are stopping here. Otherwise we can continue our balance carryover and balance distribution factor carryover, balance distribution factor carryover until getting 0, but it's close to 0. We have been seeing here it is close to 0. So now we can sum up all this value moment. Then we can found 62.75, and this point we can found 1.25 and 1.25, 1.25, 1.28, 281, 281. After getting this below, now we can draw the diagram here. We have been found 62. This is the 62 as the positive, and 125. It is also clockwise is the positive 125, as we have been shown in here the sign convention. As the sign convention, we have been seeing the clockwise is considered positive. So that's why it is taken for Hitler book. Okay, sorry. So clockwise, that is considered positive. So that's why we are taking the positive 125 here, the positive, and the minus negative 125 is anti-clockwise, and 281 is positive, and 281 negative, and 139 is positive. All the all the moment we have been drawing here. After the drawing all the moment, so what we will do after finding all the moment is here. So now we can find the reaction. How will calculate? We are taking the moment B, this point B, and 62.47. This is the 62.47, and 125 is also positive. 12 RA, this is the RA, and 12, and in 12 been found RA is minus, which is called negative downward. If RA is downward, then RB equal to upward. In the same case, we have been found here RC. This is the point of C, taking moment 125 into 28, and all this value are taking, and RB will become 107, and RY and found 113 in this way. So in from this figure we have been seen taking the moment at D, calculating, and found RC equal to 130 upward, and Fy found 139. So after getting this value, we can draw that quickly. 62, this is the 62.47 is the positive. Now we can see 125, this is the 125 negative, so this is the 125 negative, and this is the 281, this is the 281 negative also, this is the 281, and we've been found last one is 234 is positive, so that's why 234 we've been found here. All this diagram we can draw as usually, so there will be no problem. This is the but this is the shear force diagram and this is the bending moment diagram. Let's see another example. So we have been taking we are completing all this taking the stiffness is 4 EI by 8, but now we'll see the we can use the 4 EI by L instead of 3 EI. We can use 3 EI as we have been shown here. If we go to the previous slide, so here we can see we have been used K equal to 4 EI by L when the far end is fixed, but we can use 3 EI by L when the far is ruler or pin. So let's see, but you don't need to use 3 EI. Okay, so you've been seen here BA, this is the BA, so this stiffness and this stiffness will be used 4 EI by L, and this is the 4 EI by L BA and BC into 3 EI by L, because this is the pin support, that's why I have used the 3 EI by L. Then found BC value is here, so BA value is here, this is the BA, so I will get the BC will be 1 minus 0.50 as we have been shown in previously. The data that 2 will be 1, that's why I am 1 minus 1.50, this is the 0.571 and found 0.429. What will be BC? CB, this member CB, 3I by 40, because this is the fixed in moment is pin support, that's why I have used 3 EI by L and CB into CD and found 0.37. So as you know, CB and DC is 1, so that's why 1 minus 0.30 and found 0.60. And fixed in moment, as we have been shown the UDL, so W square by 2 8 and found 50. And for pin support we have been found WL PL by 8, so we have been found P is 30, L is 20 and divided by N 170 minus 75. So in this case we have been taking here distribution factor here 0.57, and this is the 0.57 we have been here. If I change the color it will be easy for you. 0.57 and this is the 0.57 and 0.425 is the 429 and 0.60 this is the 0.64 and this is the 0.36, this is the 0.6, the distribution factor, and others this is the fixed support, that's why distribution factor 0, distribution factor 0. The fixed in moment we have been taking here, the fixed in moment, this is the formula we have been shown here, 50 and 75, so this is the 50 and this is the 50 and this is the 75, this is the 75, and there is no load, that's why this is the 0. So as we know, as we have been seeing this diagram, from this diagram we have been seen here, so this is the point of B, so the B point we have been found 50 and minus 75. So if we unbalanced moment, 75 into 52 minus 25. Minus 25 into 425, it will be 10.625. If we go there, 25 into 0.425, so it will found 10.625. So in the similarly 25 into 0.571, then it will be 14.25. So how will get the 0.25? 25 is nothing but 75 minus 75 plus 40. So this is the 25. So unbalanced moment, and multiply with this, and found 45. So the carryover is always half. So if we carry over 14.275 divided by 2, then we have been found 7.48. In the same case, we have been shown here as 70. The 70, there is a 0, so 70 into 0.36, so it will be 0.27, and 70 into 0.68 into minus 0.48. So this is the 48. So it will be carry over is half. 0.48 divided by 2 is 40, and in this way we can calculate all these things, and after getting all this value, okay, so in this case we can calculate all these things and find the summation of moment after getting all this value. And after getting all this value, we can found this value and this value. Okay, so now we can put this value in diagram. So we have been seeing this is the negative, so that's why it will be anti-clockwise, minus 38.55, and positive this are, that's why clockwise 72, and minus 70 anti-clockwise, 70 clockwise, minus 50.5 anti-clockwise, and minus it will be also anti-clockwise. After getting this value, now we can taking the moment is A, and taking all the calculating all this thing, and found RB equal to 16. So RB equal to 16. We have been found this just here 16.72, and taking moment at B, and found R equal to 13. R equal to 13. Taking moment at B, found RC is 180. This is the 180. And taking moment at C in positive, RB equal to 210. And the same way, taking the moment at C, and found RD equal to 5.35, and taking moment D, and found RC equal to 5.3435 also positive. So after getting this value, we can draw the shear force diagram, and we can found the bending moment diagram also. But you can write the bending moment very cleverly. So if you draw the bending moment, assumably minus 38.55, so minus 38.55, minus 70.85, minus 70.85, minus 50.45, minus 50.45, and minus 26.75, it will be minus 20.6. So you can draw very quickly in this way, or otherwise you can draw the shear force from this diagram and then draw the bending moment. So you can see another example also. A pistis cantilever beam is having cross section given here, given the below. Analyze the beam. So you can see here, and load is given here. All the load we have been shown here, and we have been found distribution factor 16 is fixed 0. That's why AB is 0. And we can see here the BA. This is the BA, and found 0.43, and distribution factor BD. This is the BD. So you can see here, this is the DB, so reversible, it will be 1, and DE is 0, and DF also 0 as split support. Okay, so we have been shown AB is given 180, and BA WL square by 8 we have been found 1.35, and PL we have been also found, and B at this value, and all the moment we have been found in here. So member we've been seen here, the carryover is 50, 5, 5, 0 minus 1, and stiffness coefficient 3a by L we've been used here, 40a by L here and 40 by L. Distribution factor 0.43 we've been found from here, 0.597, 1 into 0. So fixing moment we've been found from here. After finding here the unbalance we've been found. The BA fixing moment is minus 1035 and BD is 630, so unbalance is minus 405. So minus 405 into 0.43, it will be 180. And in this way we can calculate all these things here. But we can use these are the basic, so we can follow this map. We will not follow the others map also. We just follow this map. If we summarize this, then we can what we can do. At first we have to we have to memorize some value which is W by 12 and W fixing moment formula which is WL square by 12 and PL by 8, and then we have to memorize 4EI by L, this, but we are not using this. And then we can, so the sign conversion is positive, and what is the fixing moment is walls and fixing board is member is called fixing moment. Distribution factor is given here. Tap by the fixed connected joint and carry the connect moment is supply the portion is resisting moment is necessary to satisfy the moment equilibrium, and joint is given all things. And member stiffness we've been seen m into k into theta, so 4EI by L, and if we multiply theta m by theta, it will be k. Okay, so the distribution factor we've been seen, distribution factor is given here, k theta by k, so it will k divided by sum of k. And then we have been seen an example also, this example. So let's see this example again. So we can calculate the distribution factor k 4EI by 12 using this formula, and distribution factor fixed support is 0 and pin support we can calculate 4EI by k into summation of k. And fixing moment WL square by 12 for the UDL and WL square by 8 for the for the vertical load. And then we can found all the value we have been seen here, BA, BC and CD, and now we can see here we have been found 240, and then we can have to balance moment coefficient, which is 50% is 120 and 50% is 120, and this carryover is 120 divided by 2 and 120 divided by 2. And here is the another moment, there is the unbalanced moment, fixing moment, which is minus 250 plus 420 240, and this will be minus 10. So minus 10 will be multiplied with minus 40, which is 4, and minus 10 into multiply into 60, it will be 6, and it will be carryover is half is 3, so it will be carryover is half is 2. Now we can recalculate here 2 into multiply to distribution factor is half is 1, and 2 into multiply with half into 1, and this is the 60 will be multiplied with the distribution factor is 0.40, it will be 24. 60 into multiply this distribution factor 1.60, it will be 36, and 36 will be carryover is half is 18, and the 24 is also carryover is half, which is 12. So after all this carryover we can found the moment. So these are the moment we have been taking all the moment. The sign conversion, we know the clockwise is positive and anti-clockwise is negative. After finding one moment, we can calculate the reaction is here, all the reaction. After getting moment in all reaction, then we can draw the bending moment diagram. So thank you everyone. If you have any question, then let me know. Thanks.